Molen, beautiful people. Today I'll be doing a topic request from an N4 student. Requested that I do go cover a statistics with engineering science. So guys, what I like us to do first, I'm the type of person who loves seeing a student excel with basics, because if you excel on the basics, it means no matter what question may come your way, you can be able to apply your mind, because for you to apply your mind in doing something, it means you must go back to the basic. So the first thing we're gonna talk about, let us talk about a moment of a force. Okay, so basically guys, I want us to talk about what is a moment. What is a moment of a force? Basically guys, this is a turning effect. Okay, this is a turning effect, okay, caused by a force now. So let us define this term, moment of a force. Suppose I have a beam, and the beam which is free to turn about a point or about this fulcrum. Okay, this is our turning point, or as we like to call it, the fulcrum. Okay, what is a moment, guys? Okay, a moment in theoretical definition is a turning effect about a point, but I like us to define it in mathematical terms. A moment, guys, is the product of the force and the perpendicular distance from the turning point to the line of action of the point of the force. Okay, so basically, guys, a moment is the product of the force and the perpendicular distance from the turning point to the line of action of the force. So basically, kasithetha nge-moment, guys, moment of a force, we are talking of a force times the perpendicular distance. Guys, I want you, every time you are solving equation of moment, to have this definition embedded in your mind. Okay, so according to what we have just defined, let me use a blue color. A moment is the product of the force and guys, and the perpendicular distance. Where is my turning point? So the first thing you ask yourself, where is my turning point? Here is my turning point. And the perpendicular distance, and this is from the turning point to the line of action of the force. Okay, is the product of the force and the perpendicular distance from the turning point to the line of action. So let us write this distance here. Ukusuka kwi-turning point ukuza apha kwi-line of action of the force. Let us write it as D. Okay. Then secondly, moments. We were obviously we're not gonna be dealing with one force only. The second thing we should know with moments is the law. It is the law. It is the law of a moment. If I'm not mistaken, it is the law of moments. Is the law of moments, because this is also important. Law of moments. Okay. The terms we won't be dealing only with one force, Okay, suppose we have a beam, okay, that is supported at this turning point, So we have force A, okay, then we have force B. Okay, guys, what this law speaks about, it speaks of a beam in equilibrium. Okay, this law states that the sum of clockwise moment is equals to the sum of anti-clockwise moment. Yeah, but what do we mean by that? For example, let us look at force A. If you see, force A will turn this beam clockwise. So the sum of a clockwise moment is equal to the sum of anti-clockwise moment. And if we look at force B, we'll turn this beam anti-clockwise. Yeah, well. So in simple terms, guys, this law states that let us just define our distances first. Okay, let's say it distance esuka apha we are to the line of action of force A, esuka from the turning point to the line of action of force A with D1. Because remember, for us to define a moment of a force, it is the product of a force and the perpendicular distance from the turning point to the line of action of the force. And let us then, for a distance force B from the line of action, let us call it D2. Basically, guys, according to this law, FA, which is the clockwise moment, moment of force FA, is equals to the moment of ubani force B, okay, which is in simple term, this is the law of moments, and this beam I movie yabo. Hence again, when we talk of law of moments, we talk of a beam that is not moving in equilibrium, meaning the forces are balanced, so this beam is not able to turn in any direction. Okay, guys, at N4 level, we don't speak of a beam in a turning point, we speak of beams that are supported. What do I mean by this? What do I mean? At N4 levels, starting a beam that is supported at 2 points. Yeah, okay. For example, this one is only supported at 1 point. That was N2, N3. Okay. In N4 level, we speak of a beam that is supported at 2 points. So at N4 level, you'll have E supports as A2. They can be positioned anywhere along the beam. Okay. Let's say this is support A, this is support B. Okay. The question that they will ask us would be to determine what value must these supports be for this beam to remain in equilibrium. Okay. So what do we do, Tina? Let's say we will take moment about each beam once at a time. You'll see when I'm doing a question, what do I mean? Let's say if I want to find what is the reaction A, I will take moments about what? I will take moments about reaction B, meaning or reaction B, I will treat it as a turning point. Then or A, I will treat it as a force. Okay, let's say I want to find a reaction value ka B. That means I will take moments about or reaction A, meaning which, guys, or reaction A will be a turning point. Then B will be acting as a force. Okay, guys, the last thing I want us to talk about before we tackle a question, I want us to talk about I want us to talk about uniformly distributed loads. Okay. Guys, I want to show you kasithetha nge-uniformly distributed load. Sithetha ngantoni, guys? Yabo. Okay, let us say we have a beam up, let us say we have a beam. This beam, let us say this beam is 8 meters long. Okay, 8 meters long. Then let us say we have a uniformly distributed load that is acting for a distance of about for a distance of about 4 meters along this beam. Okay, guys, what I have been using as far as I have started this question in terms of forces, I have been only referring to concentrated load. Yeah, but that means the line of action of that force is only concentrated in that particular point. Yeah, well, okay, it does not have an effect at any point along the beam. It only has an effect. Let's say I have a concentrated load up. Yeah, well, its effect is only along this point only, guys. Only. It's only along that point only. Okay, it's only along that point. Okay, I'm just gonna put one reaction. Let us it shouldn't be one, it should be two. I'm just gonna put one just for the purpose of demonstrating what is a uniformly distributed load. A uniformly distributed load is a force that acts along a portion of the beam, or acts along the full portion of the beam. It doesn't have to act along only a certain portion. It can act along the whole beam. For example, this uniformly distributed can be acting along the whole beam. Okay, but let us say it's acting along 4 meters of the beam. Okay, guys, let us say the distance from the left hand side to the reaction, let us say it is 6 meters. Okay, when I represent a uniformly distributed load, guys, I can represent it with a concentrated force in the middle. Okay, what do I mean? Let's say I want to represent this uniformly distributed load. I can use a single force in the middle. Let's say F1. This is the uniformly distributed load. Okay, what I mean in the middle, what do I mean in the middle? It means that since this force is acting for 4 meters, that means the concentrated load of the uniformly distributed load, I place it at the center. Okay, that means usuka apa kuyapha is 2 meters. Usuka there kuya that side, it's another 2 meter. You see that I placed the uniformly distributed load in the middle along its length. Okay, along its length. So if I were to calculate the moment of the uniformly distributed load, I would say F1. Okay, where is my turning point? Here is my turning point. What is the definition of a moment? The definition of a moment is the product of the force and the perpendicular distance from the turning point to the line of action of the force. So the line of action of the uniformly distributed load is taken, I said, is taken along the center point, along the distance which the uniformly distributed load acts. Then that means usuka from here to here, and usuka, sorry, let me use this yellow. Usuka from here to here is 2 meters, and it's another 2 meters to get to the turning point. Okay, how do I know that? The total, the total distance, and it is 6 meters, so 6 minus this 4, which is, that means this distance from here to here is what? 2 meters. So the distance from the turning point, the distance from the turning point to the line of action of the uniformly concentrated load is 4 meters. That means when I'm calculating the moment of the uniformly distributed load, is going to be F1 times 4 meters. Guys, the uniformly distributed load is normally given in a ratio form. They don't give you, they don't give you what is the concentrated load of this uniformly distributed load. They will give you in a ratio form. For example, they will say 8 newtons per meter. Okay, when you know that if I want to find what is my F1, I'm gonna say 8 times, it's this uniformly distributed load, we said it's acting for 4 meters. 8 times 8 times 4. 8 times 4, okay, which is 32, meaning my force is what? 32 newtons. Okay, when I represent it as a concentrated load. Sometimes it can be given in this ratio. Let's say 10 kilograms per meter. Okay, guys, because we are talking of a load, the first thing you have to do, because it's in kgs, I have to convert those kgs into newtons. That's the first thing I do. So I'm gonna say 10 times 9,8, because this is this is the weight. Yeah, well, the load is the weight, okay, it's gonna be 10 times 9,8. Okay, 10 times 9,8, I think that is gonna be 98 if I'm not mistaken. Okay, newtons. Then my thing now, it means now it is in, I have 98 newtons per meter. Then I take that 98 again, I multiply it by 4, and this term was uniformly distributed load is acting along the beam for 4 meters, which is gonna be, that means F11 will be F11 will be okay, sorry, times 4. is gonna be 392 newtons, okay, as a concentrated load. That means F1 will be 392 newtons. Okay, guys, now that we have dealt with a basics, let us apply those basics and solve this problem right in front of us. Okay, guys, the first thing that we're gonna do now, if we do have any uniformly distributed load, we represent it as a concentrated load at the center along the length of the uniformly distributed load. What do I mean? What do I mean by this? Sorry. If we see we have a uniformly distributed load acting along this portion of the beam, okay, and the distance of this uniformly distributed load, it acts along a distance of 5 meters, which we can see we have 1 plus 4, that is 5. So if I'm gonna represent this uniformly distributed load as a concentrated load, I'm gonna put it here in the middle, okay, and I need now to calculate its value as a concentrated load. Let us call it F1. So F1 is basically given in 5 kilonewtons per meter, and okay, if I'm gonna represent it as a force, that's gonna be 5 times what? 5. So the first 5 is the 5 kilonewton, the other 5 is the distance of 5 meters, which is equals to 25 kilonewton. So meaning if this uniformly distributed load is represented as a concentrated load at the center along the length of the uniformly distributed load, is obangani ku 25 kilonewton. Okay, now that I've gotten that out of the way, I can go about solving my diagram now. The question wants us to find the reaction forces A and B. Where are those? Here is your reaction, sorry, not A and B, sorry, reaction D and B. There are they. Okay, so let's say I want to find reaction B. That means I have to take moments about D. Meaning, guys, what does that mean? It means I'm gonna treat D as my turning point, okay, then B, I'm gonna treat it as a normal force, okay, I'm gonna treat it as a force, okay, I'm not gonna look at it as a reaction. Okay, so we're gonna apply the law of moment, okay, sum of the clockwise moment is equals to the sum of the anti-clockwise moments, okay, of which is, if I'm saying my reference point now is D, if I'm saying D is my turning point, I need to look at which forces are gonna turn this beam clockwise. Okay, if D is my reference, I see that the force B will turn this beam clockwise, and the 35 kilonewtons will turn this beam clockwise, meaning those are the two forces that are going to turn this beam clockwise when I'm saying D is my turning point. So B times, what is the distance? Yeah, well, I'm applying basics. What is the distance from the turning point to the line of action of B? That distance is what? That distance is 5 meters. So B times 5 plus, what is the other moment? The 35, the moment of the 35 kilonewtons. So I ask myself, what is the distance from the turning point to the line of action of the 35 kilonewton force? That distance is 2 meters plus 35 times 2 equals to. Then I look at the anti-clockwise moments. Okay. We see that 15, obvious now that I've sorted the clockwise moments, the remaining are anti-clockwise. Okay, so what do I look for? Okay, if I'm gonna start with the 52 Newton, usually guys, when I do this, I like to start with the force that is closest to the is to be simple, it's best to start with the force that is closest to the beam. Okay, for example, this force, the 52 kilonewton, is closest to yours, that is closest to the turning point, not to the beam, to the turning point. So 52 kilonewtons is the one that is closest to D. So that distance you can see is 1 meter. So 52 times 1. Then the next one is what? The 25 kilonewton of the uniformly distributed load. If this distance is 1, guys, what is this distance? This distance, sorry, remember, we put the concentrated load at the center, meaning the distance from here to here is 2.5 meter. Then, as remember, the total distance of this uniformly distributed load is 5 meters. What is the half of 5? Is 2.5. So from here to here, that should be another 2.5 meter. So if guys, from here to here is 1, then we go another further 2.5 to get to the uniformly distributed load as a concentrated load. That means that distance is basically 3.5. So plus 25 times 3.5 plus, then we're looking at the 15 kilonewton. Okay, usuka from the turning point ukuya ku 15, that is 1 plus 4 plus 1, that is 6 meters. You see, I'm applying basics. So 15 times 6. So what is the value of B? I'm just gonna punch on my calculator quickly to save time. That should be 52 times 1 plus 25 times 3.5 plus 15 times 6 minus 35 times 2 over 5. That is gonna be 31.9 kilonewtons. Okay, you see, simple guys. Then I want to find the value of the reaction D. That means I'm gonna take moments about B. Okay, so that I can get D. Can I just delete Shear? Okay. Okay, sorry. Okay. Now, basically, if I'm gonna take moments about B, then that means I'm treating B as my new turning point. Then I'm just gonna treat D as a force, as a normal force. Yeah, mo? Okay. We say most sum of the clockwise moment. We are applying the law of moment, is equals to the sum of the anti-clockwise moments. Okay, so if I'm saying B is my turning point, which forces are turning this beam clockwise? As I can see, the uniformly distributed load is turning this beam clockwise if B is my turning point. The 52 kilonewton is turning this beam clockwise if B is my turning point. Then the 35 kilonewton force is turning this beam clockwise if B is my turning point. Determines, I always start with the force that is closest to the turning point. So which is the 25 kilonewton. 25 times, what is the distance? You ask yourself, what is the distance from the turning point to the line of action of the force? We can see that distance. If this whole distance is what? 2,5. Basically, is 2,5 minus this distance here, which is 1. So basically, that distance should be 1,5. Okay, you see, guys, I'm applying basics. I'm applying the basic that when I'm talking of a moment of a force, it is equals to the product of the force times the perpendicular distance from the line of from the turning point to the line of action of the force. Okay, sorry guys, 1,5. Okay, 1,5 times 1,5 plus, what is the other force? The 52 kilonewton, 52. Then what is the distance from the turning point to the line of action of the 52 kilonewton? That distance is 4 meters. So times 4. Then there is the 35. What is the distance from the turning point B to 35? That distance is 4 plus 1 plus 2, that is 7, plus 35 times 7 is equals to, then the other forces are basically the anti-clockwise moments. So we have the 15 kilonewton. Okay, 15 times, what is the distance from the turning point to the line of action of that force? It is clear, it is 1, times 1 plus then the next force is the D force. D, what is the distance from the turning point B to the line of action of force D. That distance is 4 plus 1, which is 5, times 5. So what is the value of D? Let me just punch it first. Okay. The value of D would be, just punching it first, yeah. 25 times 1,5 plus 52 times 4 plus 35 times 7 minus 15 over 5. It should be 95,1 kilonewtons. Guys, after you have found the reactions, now you just have to prove your answer, guys. You have to prove your answer. For example, what do I mean by this? The sum of the downward forces should be equals to the sum of the upward forces. Okay, why is that, guys? It's because this beam, we are assuming that this beam is in equilibrium. Hence, we were applying the law of moments to solve this particular situation, to solve this particular problem. Okay, so let me add downward forces. So it's gonna be 15 plus 25 plus 52 plus 35. That is gonna be how much? 15 plus 25 plus 52 plus 35. That is gonna be 127 kilonewtons. Then the upward forces should be that amount to the sum of the upward forces. So basically this plus this, let me add 31,9 plus 95,1. 31,9 plus 95,1. That is 127. Okay, proving that our answer is correct. Okay, guys, now we're gonna do the shear force diagram. Okay, this is just a simple diagram, guys, that shows force opposite forces acting on the beam. So remember, what are those opposite forces? We have the downward forces, then we have the upward force. But this is to represent it in a diagram form. Okay, I'm just gonna highlight key things that are important when you're drawing a force diagram. Number one, a force diagram starts and end at 0. And end at 0. Then number two, a concentrated loads of force, concentrated loads of force, and reaction forces must see supports at, which is in this case B and D. We use in vertical lines. Okay, then can go 3 for a uniformly distributed load. We use diagonal lines. Okay, then we use a horizontal lines for the portion of the beam that doesn't experience any force. Okay, I will explain that that horizontal line, what we mean when I'm doing this diagram now. So guys, from your side, what you're gonna do, you're gonna draw this diagram on your book. Don't have to draw it according to scale. You are just drawing it for it to guide you as you are drawing this this shear force diagram. And what is very important in a shear force diagram is the shape. Okay, so now I'm gonna use the one that is on the question, but when you're doing it, when are you gonna draw the entire diagram? So after you draw the diagram, you use most the dotted lines. Okay, you're gonna use most the dotted lines like this. Okay, like this. Okay, you see when I'm drawing these dotted lines, I'm drawing these dotted lines where there are forces. For example, I'm drawing the dotted line for D. Okay, then I'm drawing the dotted line for the 35 kilonewton force, which is the last force. After drawing the dotted line, being guided by your beam diagram, you're gonna draw now a horizontal line. Okay, and that horizontal line represents 0. Okay, let me just highlight this, guys. A shear force diagram doesn't have arrows. Please, I don't want to see arrows. Okay, it's just lines. So I'm gonna use I'm gonna use red when I'm drawing this force, the 15 kilonewton. Then I'm gonna use pink when I'm drawing the 5 kilonewton uniformly distributed load. Then I'm gonna use green when I'm drawing the reaction force B. Then I'm gonna use blue when I'm drawing this one, the 52 kilonewton. Then I'm gonna use light green when I'm drawing the reaction force D. Then I'm gonna use orange when I'm drawing the 35 kilonewton. And notice, guys, the portion of the beam that does not have any force, and is this one and this one. I said must we use horizontal line for those, of which is we're gonna see how we do that. Okay, I said we use vertical lines for low concentrated loads and a reaction. So when I start drawing my diagram, I see that, okay, I see that I have a concentrated load that is going downwards. Okay, Don't have to draw it according to scale. And so let's say this is my 15 kilonewton. What I do now, I use negative for downwards, then positive for upwards movement. That means when I'm here, I am at negative 15 kilonewtons. Okay. Then if you look at this portion, in this portion, I have a uniformly distributed load that is acting for how many meter? It's acting for 1 meter. So basically, it's 5 times 1, which is 5 meters downwards. Your 5 kilonewtons downwards. So if I'm at 15 already, minus another 5, that means, minus another 5, that means I'll be at negative 20 kilonewtons. So I said I'm going to use a diagonal line. Okay, so this is my negative 20 kilonewtons. Then I see that I have a what? A reaction force, which is B, that is going upwards. I said I'm going to use green. What is that reaction force? Is 35.9 kilonewtons. So now I'm at negative 20 plus 31.9 kilonewtons. What is that value gonna be? Negative 20 plus 31.9, that's gonna be 11.9 kilonewton. It's gonna be positive. That means this line must jump over the negative, must jump over that reference line, which is 0 now. So let's say it's positive 11.9 is here, kilonewtons. Okay, the next force that I have is gonna be the uniformly distributed load again in this portion, which is acting for what? 4 meters. So what is gonna be? It's gonna be 5 times 4, which is gonna be negative 20. Negative, guys, means that this force is acting downwards. Remember, the uniformly distributed force is acting downwards. Minus 20. What is gonna be my value? 11.9 minus 20 is gonna be negative 8.1. So negative 8.1, let's say it's somewhere around here. It's below 15, it's below 20. So I said I use a diagonal line to draw a uniformly distributed load. Okay, that is negative 8.1. Then I see that I have a downward force, which I said I'm going to use this color of 52 kilonewtons downwards again. So minus 52, that means I'm going to be at negative 8.1 minus 52. I'm going to be at negative 60.1. So negative 60.1, definitely, remember it's not according to a scale, it's going to be here. Okay, and if you see again, along this portion of the beam, okay, along this 1 meter, I have no forces acting on the beam. What did I say? We use a horizontal line for the portion of the beam that does not, that does not experience any force. So there is no force during this along this portion. So I'm gonna use black horizontal line. So basically I am still at negative 60,1. Okay, then there's the upward force, which is D. What is the value of D? The value of D, we said it's 95,1. Okay, so we have negative 60,1 plus, it's acting upwards, most 95,1. Okay, what color am I using? I'm using light green. Okay, we're going upwards, guys. So negative 60,1 plus 95,1. That is gonna be 35. So let's say 35 is there. Okay, 35. Sorry. So 35 kilonewton. Okay, then let me look at this portion. This portion most is 2 meters, and there is no force acting along this portion of the beam, so I'm gonna use a horizontal line. Okay, then we have a downward force angle 35, which I said I'm gonna use the orange color. So if I'm at positive 35, okay, then minus 35, because I'm going downwards now, that's gonna be 0. That means if force diagram is correct, because remember I said it starts and ends at what? 0. So guys, this is my force diagram. Guys, I'm gonna ask that for me to continue posting content on this program, I need just one favor for you guys. Please like and subscribe to my content. Share my content to other students, maybe in your college, your classmates, then assist, so that I know I'm making a difference. For example, I only did a moment. I can also cover a bending moments, cantilevers, as long as I start to see, well, okay, the channel is growing, this platform is growing, so I can dedicate my time into this channel, as I'm starting to see, okay, this channel is making a difference in the community. Thank you guys, have a lovely day.